This doesn't count for my time, right?
Yeah, huh?
What? My
No,
time
we
hasn't
don't.
started yet.
We should actually start now. Let's go.
Right. Very cool.
Yes.
Great.
Alright.
So, hey guys, I'm Ryan Ju for the one person that, wow, good job, Ryan. Reset! That was my bad.
There we go.
And start over. Okay, hi guys, I'm Ryan Ju. This is my senior project, Electric ZeBras X-Ring VaNished PuG singing AO. So, from the bad title, this is, just kidding. Oh,
You have to click on the.
yeah, I got there. Here you go.
You
No?
have to click on the video.
Okay, I had a video.
Or click the little play button.
Yeah, don't worry. That's. Sorry, guys.
Try clicking space.
Ah, no, you didn't see that. Oh, by the way, can I use you in my presentation? Good. Okay, I'm gonna go and find it on YouTube, because that's what is happening. Okay, so this is what my project's about. I learned how to solve the Rubik's Cube blindfolded. And this is a competitive event that is held in just regular competitions where other people solve puzzles. And the goal of this event is to memorize a cube that is scrambled, blindfold yourself, and just solve it. So right here, I'm doing an event called Multiple Blindfolded, which is where you take at least 2 cubes, memorize them all at once, and just try and solve all of them. So I worked my way up to trying to solve 7 cubes here. So I just finished memorizing for about half an hour. And now I'm allowed to turn the cube, but I'm never allowed to take the blindfold off again until I'm done. The way it's scored is you get 1 point for every cube solved, and you lose a point if you fail to solve a cube. Right now the world record is 41 out of 41 in 53 minutes, which is crazy. This is just me. So my inspiration, obviously I've been solving the cube sighted for a while, and I just want to try a new style because this is really cool and I can compete in it, and I'm actually competing in it next week. I'm starting right away. And then
Wow.
gonna travel to New Jersey to get beaten up over there this summer. And yeah, it's really fun. So looks like I'm getting there. This was actually my 100th hour of the project, which is cool. This is probably my best attempt. And last cube.
So this is 7 cubes.
This is 7 cubes. Okay, giant pause because I got nervous. This is fast forwarded if you didn't know. No.
Those minutes are just like flying by.
Okay.
Wow.
No.
And I heard that.
Yeah.
Is
Okay.
that triumph or disappointment?
Because he missed.
Okay, so
one, like,
that means I got 6 out of 7, which translates to 5 points. If I did that in an official competition, I would be number 20 in the US. But if I got the last cube, I would have been a lot higher. Yeah, but it's unofficial, so it's cool. Now, hopefully this cooperates with me. So guys, what do you see here? This is my interactive part.
Tiger.
A tiger.
A tiger?
Forest.
Yeah, that's cool. You said one word, Marcus.
Oh.
So, what you just did there was you abstracted information from that picture, which means you just picked out information that was important. So automatically you just say like, oh, that thing, it's a tiger. And your brain has evolved to pick out what's important because that was a 16 kilobyte image, but you just said like, oh, that's a tiger. Some things were important, like if you noticed the tree or something, the tiger would have killed you, and that sucks. So abstract algebra, it uses abstraction as well, which is just picking out what's important from a problem. So abstract algebra doesn't mean it doesn't exist. It means it's just abstract. So regular math too is also abstract because numbers, well, it's debatable, but they don't really exist. It's what you pick out from the problem so you can focus on what's important to the problem. So, Marcus, abstract algebra exists.
Okay.
Yeah. Okay.
I don't even remember that conversation we had.
Dude, you're in. So, a lot of math all of math, it's based on axioms, which we learn in geometry. It's like you start with things that you don't have to prove, and from there you make theorems, and from that you can make problems. But there's more than one algebra. There's a lot of different math for different situations. So if you were adding up two pieces of pie, you would make common denominator when you're adding two fractions. But let's just say you're taking a batting average. You wouldn't do that because then you get averages way over 1, which doesn't make sense for the problem. So you want to add the top and bottom. And then every algebra has just a bunch of different theorems and axioms that may not make sense to other problems, but it makes sense in the context of the problem. So this is just fun stuff I found. So in abstract algebra, we don't really care about the functions exactly. We have a bunch of elements, and those elements have functions performed to them, but we just abstract that. We say, okay, well, what if we just think about it more generally? So we generalize things to structures such as groups, rings, and fields, which I'll get to later. And one of my mentors was a PhD in math, and I asked him, if I only know calculus, can I learn abstract algebra? He's like, well, yeah, because abstract algebra doesn't depend on functions. You don't have to know how they work. You just have to be able to think differently from what you know. So even though abstract algebra is generally learned at a higher level of math, I was able to do it because it's just not really a continuation. So the Rubik's Cube, as a puzzle, it forms a group. And a group, there's only 4 rules. It has to have closure, which means all the elements in the group plus a function end up with another member of the group. So if you just keep turning a cube, you will always end up with a legal position in the group. And then there's associativity, which is that axiom right there. If you just say like, oh, I'll do A plus B plus C, that's the same as doing A plus B plus C. So you can put parentheses around a set of moves.
So what you're calling plus is really a turning of the cube?
Yeah, the plus is just any function. So it's consecutive
turn
turning
cube is a turn?
Yeah.
Okay.
It's a turn or a series of turns. So then we have identities, which means there's certain things on the cube that won't do anything. So if I turn a cube and turn it back, that's an identity. Or if I turn the cube 4 times, that's an identity, because you end up with the same thing. And then you have inverses. So you can, again, turn a cube once, turn it back, that's an inverse. You do something, undo it. So since the cube follows all those rules, you know it's a group, and you could study group theory and then apply that to a cube, rather than studying the cube itself. So one theorem from group theory is Cayley's theorem, and it states that every group is isomorphic to a group of permutations. So an isomorphism is just something, it's 2 problems that are the same, but they just look different. So the group I comma multiplication is isomorphic to something called mod 4. What that means is if you multiply I by itself, you end up with a cycle. You get I, -1, -I1, and then you just keep multiplying that, and you'll get the same thing. And the cube is isomorphic to that, because if you keep turning the top layer like this, every 4 you'll get the same thing. So those problems are isomorphic to each other. So you can study the underlying structure rather than the function itself. Okay, so if you take apart a cube, you end up with this central core, which we just keep constant. Then you probably can't see that very well, but that's an edge piece, and those have 2 stickers on them, and they always end up in a spot where an edge goes. Like all edges will end up in another edge place, so they just interact with each other. And you have corners, and they do the same thing. There's 8 of them. They switch around, and they'll always end up in a corner position. So you can study how they permute, because according to Cayley's theorem, they're all isomorphic to permutations. So if you go on and study the permutation of something, let's just say you have the elements A through I, and then you scramble them. Well, you can look at it like this, but you can also decompose it into what we call cycles. So like A, it went to where B goes, and then B went to where F goes, F went to C, C went to A, and that just goes in a circle. So A to B to F to C to A, you could represent it like that. And then same with the rest of the scramble. So since the cube is a group, it's isomorphic to permutation, you could study what the cycles do rather than just arbitrary stickers. Okay, so kind of just said that, but cube is a function. It has elements, and you move them around. Forms a group, so it's isomorphic to permutations. And then you could decompose this permutation into cycles. And since all groups have inverses, you can simply invert the cycles and memorize that to solve a cube. That's Stefan Bachmann. He invented one of the beginner methods for blind solving, which I use. And that's Tyson Mao. He was the first one to solve it blindfolded in under 2 minutes. And he founded the World Cube Association, so it's cool. But now he's married. Okay. So, which of these have you seen before? Anyone?
The one on the right.
Yeah, okay. Which two have you seen before?
No, but this is red X. So
Yeah.
it's 0
Yeah.
to 2.
And the zebra.
Okay. And which two have you seen before?
So, good God.
Okay. Seen that one before?
Yes.
Yeah. Okay. So unless you stop Lucy, you haven't seen that in the picture. So you have seen that before probably because you're American, and I just showed you that. So what I was trying to demonstrate there was people, whether they know it or not, they have really good memory for images, and that's really important. So when you have a cube, even if you abstract it to inverse cycles, you'll end up with something ugly like that. That's just for the edges of a cube, not even the corners. So if you just try and brute that, that's not cool because it won't work. Because human memory isn't really linear. It's not like a computer where it's just like, remember that. It's you might remember something for a weird reason. So my excuse for wearing this is it has nothing to do with my presentation, but you might remember my presentation because I wore something weird. And also you have a limited space you can remember. So magic number is 7 plus or minus 2. So you can keep track of like 5 to 9 things. But if you get distracted, you might just lose it all. So you don't want to have to keep track of too many things. That's the book I read about memory. It's really cool. You should check it out. It's in the bibliography. Okay, so as I was saying, you have really good image memory. So there have been tests where people are just shown images, like 10,000 of them, every few, just a few seconds at a time. And then a month later, they have 95% recall. Just because even if you don't remember the image, if you see it again, you're like, oh, I've seen that before. Like my friends, I have 500 images that are memes that I constantly reuse, and they notice because they just remember. They know they've seen them before. You can remember your senses really well. You can remember spaces really well because if you walk into a room, that's a lot of information actually, but you don't realize it. It's just like, ugh. But if you were to put that in Google Sketch, that's a lot of information. And then people can remember processes well. So even people with amnesia, they can maybe like walk around the neighborhood and eat and just do regular things, but they don't really declaratively remember it. They're just like, oh, I'm just doing it. I just know. And then what we're bad at remembering stuff, it's abstract stuff. So just random letters or numbers, we're just like, eh. And then isolated things. So the way to illustrate this is, it's called the Baker/Baker test. So if you say something like, oh, this guy's name is Baker, people might not remember, but if you say this guy is a baker, then they'll think of him like baking bread, so you have some context, and they're more likely to remember. So that's why I always introduce myself with my full name, because they can think of Jews, and Ryan's a common name, so that doesn't work. So, yeah. Okay, and in Moonwalking with Einstein, the book I read, they talked about this condition called synesthesia, where people, they perceive abstract things in different ways. So if you say like 37, they get these colors and senses and images in their mind. So like 87, they might think of like an old woman wearing a diaper or something. And it's just how they perceive it. And since it goes from an abstract to a concrete, they just remember things really well. And it's weird like that. So another way to get over your memory is you can chunk information together. So since you have a finite number of things you keep track of, you can just consider them different things, or smaller things. So this string of numbers here, it's just a string of numbers, but this day here, it's the European way of saying the day we land on the moon. And then the next one is Pearl Harbor. So if you just remember two things, you can just translate to that. And same thing with this algorithm. When cubers remember algorithms, they often remember them in things called triggers, which are just movements. So it'll be like, okay, move it like this, and that might be 4 moves. So this can be thought of as like 4 things rather than 16, which is too much to remember. Okay, so what we do to abstract is we take our letters, we put them in pairs, and then we just think of each pair as some image. So I've translated each of these pairs into an image, but we can go even further because you can make it even worse. This is something that came up in a blind solve once. So WTAK, white AK-47, that's right there. And then DH is Dr. Hogarty, and then GS is gas, and I made that a verb, so he's gassing. And then he's gassing Matthew Escobar's testicles. And then you have to really step into this image and imagine it, and it's hard to forget. In fact, I didn't make this presentation until a couple weeks after I had that solved, and I still remembered it. So since I put it in all these terms of senses, I just remembered it because it was so vivid. Yeah. So over time, you develop something called memory matrix. It's kind of ugly and this isn't even accurate, but it's every combination of letters I could possibly get. And there's a lot of combinations, but it's just something you have to work on. So when you're forming these images, they have to just fit you. And you don't have to tell anyone your memorizations. It's just I choose to because they're disturbing. So when I get BK, I think of Burger King, and that's cool because like I know Burger King, like I go there all the time. I can just relate to it. But I used to use berkelium, the element, and I really that's abstract to me. I don't know what it is, so I shouldn't use that. And then this is my image pair for UA. It's because this is a song and they make the ooh-ah sound, so I just make that UA for me. But for someone else, if they don't know the song, then it doesn't make sense. And then you have to make sure that you can cover everything. So versatile images are nice, like piss, because that's a verb, it's a noun. It can be an adjective if you make it one. And then I use kill, that's the guy who sings the troll song. So it can be really audio-based, or it could be someone singing the troll song, or it could be him. And then you can also pick multiple images for one letter pair. So like for AO, I use singing AO, like from the title. Or I also use Chinese character for Australian, so I can think of an Australian guy, or it can be an adjective, the guy is Australian. And you have to make sure you don't repeat things. So Alan Harper, I don't use for AH because I already have that reserved for Adolf Hitler. And so if I get Alan Harper and I'm like, oh shoot, what was that? That's always AL. So I never repeat things. Okay, so I'm gonna go ahead and do a solve. I actually have it scrambled ready. This was from my best solve, which was 129 in the chem lab for some reason. And yeah, I already have it memorized. So I'm just gonna talk through it. Okay. So I've memorized it, and then I always start from this piece, and it needs to go to position F, which I've designated. So the first image is the feds axing Jet Li. So the feds is FD. Okay, and then they're axing him. So A, X, and then J. And then I try to make all the edges one image, but in this case I was doing it on the fly and I was doing it really fast. So I just made a second image so that I had KC, so that's K, C, and then she was rowing. Okay, and then I should be onto corners now. So it was GU, which is Emily Gu, and then her kinetic energy, KE, was singing AM. So she's like just really hyper and she's singing. So G, U, and then K, E, A, oh, a corner that was going to be turned, and I just go like this, like I do a physical action, so I just flip them at the end. And if that was right, yeah.
We're going to take it up, but on that note, that's actually a great place for us to stop.
Okay, yeah, that was actually my last slide, basically, like,
Perfect.
yeah.
So, we should move to the theater now. Let's give Ryan a big hand though. That was amazing. I am grateful for that tour of your imagination.
Oh no, I'm not even done. You've done some terrible things, Mr. Dula.
I do not
You've done terrible,
know
terrible things.
other algorithms you use for solving that cube.
Okay, yeah, if you could bring the cubes down here, that'd be nice.
Let's bring the cubes down and
Yeah.
perhaps go to confession after this. Good.
Don't worry, I had to take my mom out of my matrix because I can't remember that stuff.